Tesla just opened the blueprints to its most advanced motor, and every automaker unearthed them, none of them can build it. That's not a flex, that's a gap. A carbon fiber sleeve, 2.5 millimeters thick, spinning at 320,000 RPM without deforming by a single micron. The design is public. The machine that makes it doesn't exist anywhere else on the planet. Toyota can't replicate it. Volkswagen can't replicate it. BYD, the company that outsold Tesla last year, can't replicate it either. And here's what nobody is saying out loud yet. This motor was never built for the car. To understand why the carbon sleeve rotor matters, you need to go inside a motor, specifically to the part that has quietly limited every electric vehicle ever built. In virtually every EV motor on the road today, the rotor is built from copper windings bonded to a silicon steel core. These materials have worked reliably for over a century, but they carry a ceiling that physics enforces without negotiation. As rotational speed increases, centrifugal forces acting on the rotor multiply exponentially. Around 18,000 RPM, those forces begin to exceed the yield strength of silicon steel, approximately 350 megapascals. The metal distorts. Microscopic imbalances generate heat and vibration. Efficiency collapses precisely at the moment the driver demands peak performance. Tesla's answer sounds deceptively simple. Wrap the rotor in carbon fiber. But the engineering required to actually do that at production scale is one of the most demanding manufacturing problems the company has ever attempted to solve. Carbon fiber carries a tensile strength exceeding 400 megapascals, more than 3 times that of Inconel 718, the superalloy used in jet engine components. The sleeve itself is only 2.5 millimeters thick. Under compression, it applies a calculated inward preload that holds the rotor rigid through 22,000 RPM, sustained, not peak, sustained. The result is a motor that maintains near-perfect dimensional stability from a cold start through extended highway acceleration. No distortion, no efficiency cliff, no thermal spiral when you need every watt the system can deliver. The downstream consequences of that stability are significant. When the rotor holds tighter tolerances at high speed, the air gap between rotor and stator, the invisible space where electromagnetic force is actually generated, can be reduced by approximately 50%. That narrower gap cuts peak current draw by an estimated 15 to 20% and increases torque output by 25 to 30%. A cooler running motor also reduces the parasitic load on the thermal management system, which extends range, which reduces charging frequency, which reduces total grid demand across an entire fleet. One component, every system it touches shifts with it. Tesla opened its carbon sleeving patents to the public. Any engineer on Earth can download the full design documents and study every dimension. Elon Musk framed this as generosity toward the broader EV industry. It is not generosity, it is a demonstration of distance. There is a fundamental difference between knowing a recipe and running a restaurant. A Michelin-starred dish might be documented in a published cookbook, but the technique, the timing, the calibrated equipment, the instinct built through 10,000 repetitions, none of that transfers with ink on a page. Tesla's carbon sleeving process requires a robotic winding system guided by artificial intelligence, capable of applying fiber at micrometer-level precision, not millimeter. Micrometer 1,000th of a millimeter. That system simultaneously monitors fiber tension, ambient temperature, winding angle, and linear speed in real time. After each rotor is wound, a laser inspection array scans for deviation before the component ever reaches the assembly line. The machine adjusts tension hundreds of times per second, compensating for thermal drift in the fiber itself. Each rotor is verified against tolerances measured in fractions of a micron, then logged in a digital twin that follows it through every subsequent production step. You can read every patent Tesla has ever filed. You still do not have the machine. You do not have the AI training data built from thousands of failed rotors that taught the system where the failure modes hide. You do not have the production infrastructure to replicate this at 40,000 units per month. Tesla published the finish line. What they kept private is the track, the training program, and the decade of institutional knowledge that built the runner. Opening the patents was not an invitation. It was proof that the gap cannot be closed by reading. The motor itself is one layer of the story. The competitive picture surrounding it is another. BYD surpassed Tesla in global EV sales by unit volume and operates a vertically integrated supply chain that includes its own batteries, its own chips, and its own motor components. Its production costs are materially lower. The company is expanding aggressively into Europe, Latin America, and Southeast Asia. The primary barrier remaining is brand recognition and regulatory access in the United States, where tariff policy has so far limited direct competition. Trade environments, however, have shifted faster than most projections anticipated. Lucid Motors holds genuine engineering credibility. The Lucid Air drivetrain is sophisticated, and its range figures exceeding 500 miles remain ahead of the Model S. But Lucid sells into an ultra-luxury niche measured in thousands of units. That is not a market position from which you fund the research required to close a motor technology gap at scale. Ford and General Motors, despite combined electrification investments approaching $50 billion, remain dependent on external battery and motor suppliers. Neither company can concentrate its entire technological bet the way a pure-play EV manufacturer can. The competitive map at this moment follows a consistent pattern. The company with the engineering lacks the scale. The company with the scale lacks the brand. The companies with the brand lack both. Tesla currently holds all three, and has now added a motor that no competitor can manufacture at volume even with unrestricted access to the design documents. During the Plaid unveiling, Elon Musk made a comment that received almost no attention because the audience was focused on acceleration figures. He noted that the motor's power-to-weight ratio, thermal stability, and sustained high RPM capability made it suitable for applications significantly beyond passenger vehicles. That comment deserves to be taken seriously. The electric aviation sector, specifically eVTOL urban air mobility, has been bottlenecked by exactly the problem the Plaid motor solves. Propulsion systems for vertical takeoff aircraft need to be light enough to preserve payload capacity, powerful enough to maintain lift under load, and thermally stable enough to survive repeated high-intensity cycles without degradation. Every major eVTOL developer is hitting the same wall. Conventional electric motors are either too heavy or too thermally unstable for sustained urban flight operations. A motor that weighs less because its rotor is structurally lighter, spins beyond 20,000 RPM without deforming, maintains compressive integrity across extreme temperature swings, and can be manufactured at industrial scale. That is not simply a better car motor. That is a solution to a problem that has been stalling a multi-billion-dollar aviation sector for 5 years. Tesla has made no formal announcement regarding aviation licensing, but Musk's public statements and supply chain signals point in a direction that is difficult to misread. For companies in the eVTOL space, the silence is not reassuring. It is the kind of silence that typically precedes a shipping announcement. Meanwhile, Tesla signed a $5 billion deal with NAT Power in June 2026 to deploy 25 gigawatt-hours of Megapack battery storage across the United Kingdom and Italy. Its Lathrop facility now produces Megapack systems at 40 gigawatt-hours per year. Combined with the Autobidder software platform, which autonomously trades stored energy on wholesale electricity markets, Tesla is no longer operating as an automaker that also sells batteries. It is operating as a managed energy infrastructure platform that also sells cars. Every competitor benchmarking against the Plaid motor is solving last year's problem. The carbon sleeve rotor is a genuine engineering achievement. The tensile strength figures are real. The thermal stability data is real. The production gap between Tesla's AI-guided winding system and anything a rival can deploy within the next 24 months is real. But the rotor is not the story. It is the most visible symbol of a larger transition from automaker to energy infrastructure company that most of the world has not yet registered. History has a way of humbling sophisticated predictions. Betamax was the superior format. The BlackBerry keyboard was objectively better than any touchscreen in 2007. Nokia dominated mobile phone sales until, almost overnight, it did not. Engineering excellence does not guarantee market permanence. So here is the question worth sitting with. Many mechanical engineers argue that pushing a consumer motor to 22,000 RPM is a long-term durability gamble, a performance headline that trades sustained reliability for a launch event. Meanwhile, companies like Toyota are betting their electrification future on solid-state battery architecture. Slower, more conservative, but potentially transformative in ways that sidestep the motor debate entirely. Which side are you on? The realist camp or the tech camp? Drop your position in the comments. And if this analysis showed you something the headline coverage missed, subscribe, because the next video goes deeper into the solid-state battery race and why that outcome may ultimately matter more than any single motor ever could.